A pure substance is one which has a fixed chemical composition throughout. Water, nitrogen, helium, and carbon dioxide, for example, are all pure substances. A pure substance may exist in more than one phase, but the chemical composition is the same in all phases. So, liquid water, a mixture of liquid water and water vapor, and a mixture of ice and liquid water are all pure substances, because no matter where you take a sample of molecules from in any of the mixtures, you would still have the same molecule, H2O. There are many situations where two different phases of a pure substance coexist in equilibrium. For example, in a boiler, water exists as a mixture of liquid and vapor. In this video, we're going to focus on the liquid and vapor phases of pure substances and their mixtures. We're going to use water to demonstrate this, since it is the substance we are most familiar with. To give a visual representation, we're going to consider a fixed mass of water within a container at a temperature of 20 degrees Celsius. This mass of water is restricted above by a piston and is kept at a pressure of 1 atmosphere at all times. We're also going to illustrate the temperature and specific volume of the liquid graphically. Under these conditions, at this state, water exists in the liquid phase and it is called a compressed or subcooled liquid, meaning it is not about to vaporize. If we transfer heat to the water, we'll notice that its temperature begins to rise. And as the temperature rises, the liquid starts to expand, causing its specific volume to increase as well. And this causes the piston to rise slightly. Let's say we heat the liquid up to a temperature of 50 degrees Celsius for now. The pressure of the liquid is still kept constant at 1 atmosphere throughout this process. And at this state, the liquid is still a compressed liquid because it is not about to vaporize yet. As more heat is applied, the temperature will continue to rise until it reaches 100 degrees Celsius. At this point, water is still a liquid, but any further addition of heat will cause some of the liquid to vaporize. A liquid about to vaporize is called a saturated liquid, and so this state is called a saturated liquid state. Once boiling starts, there will be no further increase in temperature until all of the liquid is completely vaporized, assuming the pressure remains constant. The only observable change during boiling is a large increase in the volume and a reduction in the liquid content as more and more liquid is converted into vapor. At this intermediate state, where there is a mixture of liquid and vapor, the substance is called a saturated liquid-vapor mixture. Now, we've applied more heat, and the last of the liquid has just been vaporized. At this point, the entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat loss from this vapor will cause some of it to condense, and a vapor about to condense is called a saturated vapor, and so we call this state the saturated vapor state. We now have just one phase, which is vapor. Any further heating will cause an increase in temperature and expansion, which means a corresponding increase in specific volume. Now, if we remove any heat from the vapor, we'll see a decrease in temperature, but no condensation, as long as the temperature doesn't drop back to 100 degrees Celsius. A vapor which is not about to condense is called a superheated vapor. So the water at this state is a superheated vapor. Now, to quickly recap, we heated up our liquid from 20 degrees Celsius to 100 degrees Celsius. And up until this point, it was a compressed liquid or subcooled liquid. At 100 degrees Celsius, the liquid becomes saturated because some of it is just about to start vaporizing. Beyond this point, temperature remains constant although heating continues. And as more and more of the liquid vaporizes, we have a mixture of liquid and vapor called a saturated liquid-vapor mixture. Once all the liquid has been vaporized, we arrive at a state called the saturated vapor state. Any further heating increases the temperature of our vapor and it becomes a superheated vapor. Diagrams make it a lot easier for us to study the phase change processes that pure substances undergo. We're going to start with the TV diagram, which is a graph of temperature against specific volume. And that's because we've just seen how the diagram of temperature against specific volume shows the conversion of water from compressed liquid to superheated vapor at the standard pressure of 1 atmosphere. This phase change process occurs in a slightly different manner at different pressures as shown in this diagram. Boiling, which happens when the substance becomes a saturated liquid and starts vaporizing, occurs at temperatures higher than 100 degrees Celsius for pressures greater than 1 atmosphere, and at temperatures lower than 100 degrees Celsius for pressures lower than 1 atmosphere. So, for different pressures, phase change takes different but similar looking paths on the temperature against specific volume diagram. We also see that as pressure increases, the saturation line, which is the line between the saturated liquid and saturated vapor points, starts to shrink. If we continue this, we get to a pressure where, instead of a line, we get a point at which the saturated liquid and saturated vapor states are identical. This point is called the critical point. The temperature, pressure, and specific volume of a substance at the critical point are called the critical temperature, the critical pressure, and critical specific volume, respectively. At pressures above the critical pressure, there is no distinct phase change process. Instead, as we heat the liquid, its specific volume continues to increase, and eventually, it resembles a vapor, but we can never tell exactly when the phase change occurs. We can connect all the saturated liquid states by a line called the saturated liquid line, and the saturated vapor states by another line called the saturated vapor line. These two lines meet at the critical point, forming a dome. To the left of the saturated liquid line, we have the compressed liquid region, and to the right of the saturated vapor line, we have the superheated vapor region. In both of these regions, the substance exists as either a liquid or vapor. Under the dome, we have the saturated liquid vapor mixture region, where the liquid and vapor states exist in equilibrium. Next up, we're going to talk about the PV diagram, which is the graph of pressure against specific volume. The general shape of the PV diagram of a pure substance is very similar to the TV diagram, but the temperature constant lines have a downward trend. Finally, we're going to talk about the PT diagram, which is the graph of pressure against temperature. The PT diagram shows the pressure-temperature combinations that result in a phase change. For example, 1 atmosphere or 0.1013 megapascals corresponds to 100 degrees Celsius for water in phase change from liquid to gas or vapor. Likewise, 0.4762 megapascals corresponds to 150 degrees Celsius for water in phase change from liquid to vapor. This diagram is often called the phase diagram since all three phases are separated from each other by three lines. The sublimation line separates the solid and vapor regions. The vaporization line separates the liquid and vapor regions, and the fusion line separates the solid and liquid regions. These three lines meet at the triple point, where all three phases coexist in equilibrium. The vaporization line ends at the critical point, because no distinction can be made between liquid and vapor phases above the critical point. Any equation that relates the pressure, temperature, and specific volume of a substance is called an equation of state. There are several equations of state. Some are simple and some are complex. The simplest known equation of state is the ideal gas equation of state, and it accurately predicts the PVT behavior of a gas at certain states. The ideal gas equation of state is given as PV equals RT, where P is the pressure, V is the specific volume, T is the temperature, and R is a constant called the gas constant of the substance. The gas constant R is different for every gas, and it is obtained by dividing the universal gas constant Ru by the molar mass of the gas. The universal gas constant has the same value regardless of the gas, and in SI units it is given as 8.31447, and its unit is kilojoules per kilomole Kelvin. The molar mass, m, can be defined as the mass of 1 mole of a substance in grams or the mass of 1 kilomole in kilograms. Any gas which obeys the ideal gas equation is called an ideal gas. And we can rewrite the ideal gas equation as R equals PV divided by T. So, for two different states of the same gas, we can write P1V1 divided by T1 equals P2V2 divided by T2. And if we're dealing with the same mass of gas in both states, then we can multiply both sides by mass. So instead of specific volume, we use total volume. Also, whenever we use this relation, we have to convert our temperature to an absolute scale, like the Kelvin scale. So let's solve some problems on the ideal gas equation. The gauge pressure of an automobile tire is measured to be 210 kilopascals before a trip and 220 kilopascals after the trip at a location where the atmospheric pressure is 95 kilopascals. Assuming the volume of the tire remains constant and the air temperature before the trip is 25 degrees Celsius, determine the temperature in the tire after the trip. Firstly, we've been given the two pressures, and we know that the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. So our initial pressure, P1, is equal to 210, which is the gauge pressure, plus 95, which is the atmospheric pressure, and this gives us 305 kilopascals. Similarly, our final pressure, P2, equals 220 plus 95, and this gives us 315 kilopascals. Our initial temperature is 25 degrees Celsius, and to convert that to the Kelvin scale, we add 273.15 Kelvin to it, and so we have 298.15 Kelvin as our initial temperature. So using our ideal gas equation, we have P1V1 divided by T1 equals P2V2 divided by T2. So substituting our known values, we have V1, V2, and T2 unknown. The volume remains constant, so we can just cancel both volumes out on both sides of the equation, and we're left with T2 as our only unknown. So solving for T2, we obtain T2 as 307.93 Kelvin, and converting that to the Celsius scale, we have 34.78 degrees Celsius. For our second problem, a quantity of gas has a pressure of 350 kilopascals when its volume is 0.03 meters cubed, and its temperature is 35 degrees Celsius. If the value of R, its gas constant, equals 0.29 kilojoules per kilogram Kelvin, determine the mass of the gas present. And if the pressure of this gas is now increased to 1.05 megapascals while the volume remains constant, what will be the new temperature of the gas? So solving this, we're going to write out our known values. So we know P1, which is equal to 350 kilopascals, V1, 0.03 meters cubed, T1, 35 degrees Celsius, or in the Kelvin scale, 308.15 Kelvin, and R equals 0.29 kilojoules per kilogram Kelvin. And we know P2 as 1.05 megapascals. Converting that to kilopascals, we have 1005 kilopascals. And our V2 is 0.03 meters cubed as well, since the volume remains constant. T2 is unknown. To find the mass of the gas present, we are first going to find the specific volume of the gas using PV equals RT. So rearranging this equation, we have V equals RT divided by P. And then we substitute our known values of R, T1, and P1. And we obtain V, which is the specific volume, to be 0.255 meters cubed per kg. It's also important to make sure your units are consistent before you start solving. So the unit for R, kilojoules per kilogram Kelvin, corresponds to kilopascals for pressure, Kelvin for temperature, and meters cubed per kg for specific volume. Now, to find the mass, we know that the mass of a gas or any substance equals its total volume divided by its specific volume. And we know the total volume and specific volume of the gas in this case. So we substitute in our values to find the mass, and we obtain 0.118 kilograms as our mass. Now to find T2, we can use P1V1 divided by T1 equals P2V2 divided by T2. Again, we can cancel out the volume from both sides because the volume remains constant in both cases. And we also have a constant mass in the two states. So we're left with P1 divided by T1 equals P2 divided by T2. Substituting our known values, the only unknown we have here is T2. And again, we make sure our units are consistent, having our pressure in kilopascals on both sides. So solving for T2, we have 884.83 Kelvin. Or converting to the Celsius scale, we have 611.67 degrees Celsius. For our final problem on ideal gas equation, a vessel of volume 0.2 meters cubed contains nitrogen at 1.013 bar and 15 degrees Celsius. If 0.2 kilograms of nitrogen is now pumped into the vessel, calculate the new pressure when the vessel has returned to its initial temperature. The molar mass of nitrogen is 28 kilograms per kilomole, and it may be assumed to be a perfect gas. So, to start solving, we first write down what we know. We know the initial volume, which is the volume of the vessel, and it is 0.2 meters cubed. We know the initial pressure, 1.013 bar, or 101.3 kilopascals. We know the initial temperature, 15 degrees Celsius, or in Kelvin, 288.15 Kelvin. The final volume, or the volume after the gas has been pumped in, is still 0.2 meters cubed. And this is because the gas is contained in the vessel, and it will always expand to fill the volume of its container. So the volume of the gas is going to be constant. We don't know P2, but we know T2 to be 15 degrees Celsius or 288.15 Kelvin, the same as T1, because we were told that the temperature returns to its initial temperature. We were also given the molar mass of nitrogen, which is 28 kilograms per kilomole. We can calculate the gas constant for nitrogen, R, and we use R equals Ru divided by M, which is the universal gas constant divided by the molar mass. So our gas constant is 0.297 kilojoules per kilogram Kelvin. To find P2, our final pressure, we use P1V1 divided by T1 equals P2V2 divided by T2. But we were told that in the second state, 0.2 kilograms of nitrogen was pumped into the vessel. So even if V1 and V2 are the same, we can't use this equation this way because we're not dealing with the same mass in both states. We instead have to use the specific volumes. So to find V1, the specific volume in the initial state, we can use PV equals RT. And rewriting this, we have V1 equals RT1 divided by P1. Substituting our values for R, T1, and P1, we obtain V1 to be 0.845 meters cubed per kg. We can't find V2 in the same manner because we don't know P2. And the whole point of our solution is to find P2. However, we can find V2 using the total volume and the total mass. We know that specific volume equals total volume divided by total mass. And we know V2 equals 0.2 meters cubed, the volume of the vessel. M2, which is the mass of the gas in the final state, equals M1, its mass in the initial state, plus 0.2, which is the additional mass of gas added. We know that the mass of a gas or a substance equals its total volume divided by its specific volume, so we can use this to find M1. And we obtain M1 to be 0.237 kilograms. So M2 equals 0.237 plus 0.2, which equals 0.437 kilograms. And V2 equals 0.2 divided by 0.437, which gives us 0.458 meters cubed per kilogram, approximately. So back to our ideal gas equation. P1V1 divided by T1 equals P2V2 divided by T2. We can cancel out T1 and T2 in both sides because T1 and T2 are the same. So we're left with P1V1 equals P2V2. And substituting our known values, we have P2 as our only unknown. And we obtain P2 as 186.9 kilopascals.